Okay, so for this last lecture, here is a proof that I'm a bit tired because I just forget to change the title, but it's not about elliptic curve, it's about L function. So you have to know that in validity, if you want to define an L function, you have only one function to remember, which is L create. With this function, the input will determine which kind of L function you are creating. If you just want the Riemann zeta function, just write L create of 1. Okay, this is the Riemann zeta function. You can also have it with zeta function. If you want to look at an L function for a Dirichlet L function for a quadratic character like that, just mention B. If you want Dirichlet L series, just specify the modulus. For detecting L function, so attached to a number field, you just specify the polynomial, which defines your number field, and so on. So for elliptic curve, you just give the elliptic curve, and the software will understand what you want to do. And after that, you can initialize your L function with alpha limits. Inside alpha limit, you will give your L function, so L creates something, and you can specify a domain, which is a rectangle, which is centered on the real axis, so you have some height and some width. And so you specify the center and the number on the real axis, then the width, then the height of your domain. You have some shortcuts. Just specify the height if you just want to be on the vertical line. And it will be the critical line here. And if you just want some values for real, you set h to 0 so that you don't have any height on the real line. So when you write L create of something, you get this kind of stuff, which is L function. It's a Dirichlet series, and the output is huge and contains the coefficient of this series, the Dirichlet coefficient of your dual L function. If it's the same than this one, it will just be written 0. Okay, and you get also the number to define your gamma factor, Euler gamma factor. You will have the weight k. That means the value, the k for okay. In your functional equation, you have some values that are related, values at s and values at k minus s. The weight is this k. You also have the conductor of your L function, the root number, and the polar part. So, for example, if you want to use the Riemann zeta function, to create it, you use L create 1 because it's Riemann zeta function. It gives you that, so that means that every coefficient here is 1. The coefficients for the dual L function are the same than this one. So that was the number that defines the gamma factor, which is this here 0, you have none. And 1, 1, 1 is weight conductor number and polar parts. So this is really easy. You can ask for the 21st coefficient of your series. So alpha an is the name of this coefficient here. You ask for the 21st one. Here you will have like a sequence of 21. You can ask for L of 2, alpha And then here you specify the name of your L function given by L create. Then the value of S. You get L of S. You can also have the values of your derivative. Here, the first derivative of data, so it's data in French. I don't know the name of the sign. Of 0, you get this number. If you ask for your data function at 1, you know that it will not converge. So you have something like that that says that there is a problem. You can also add value at okay, I don't know the English name of this kind of expression. Yeah, your big O plus a polynomial. Let's say that. You can ask for the zeros of your F function up to some height. So you have a list. Here, I have just this one. So I have just 1 0 up to this height. So this is the value of the imaginary part of your. The real part is 1/2, because you are on the physical line. And you can also add value of your complete L function. So this is a big lambda. So you can ask for value, and you can, if you want, check the functional equation on this big lambda step. So if you want the L function attached to a Dirichlet character, so this shape, you first have to generate this character. For that, you look at Zn star for 1 means that you are looking for Z/4 star. Okay. The one here is an optional argument that gives you the class group, I mean the structure of this group. So here the one is just like technical stuff. So here we get that this is a group of order 2 generated by 2. I mean it's Z/2Z, this structure. And here it's a generator. You can then create your L function giving a vector of with 2 components, G, and here it's your character. So 1 here is the only non-trivial character on this group. Of this group, it's like if you have to write it, you know, it's a 4-cycle character which takes the value 1 0 minus 1 0 and so on. So here I ask for the coefficient of the dual L function. It tells me that this is 0. I mean, the same than your original L function. Then it's here the number that comes defining the Euler gamma factor. It's just 1. Okay, I forget it, but I got it right. So your so here the Dirichlet character is this one. Okay, so the dual function has the same coefficient than your original L function, which is in fact the beta function. You have only one term that defines your factor product, is 1. So your gamma product is here, your gamma factor is here. The functional equation relates value at S and 1 minus S. This is this one here. And finally, the conductor is n equals 4. And so you can define your big lambda like that. You can ask for the first coefficient of your Dirichlet series, and you see that this is 1 0 minus 1 0 1 0 minus 1 0. It's the successive values of your character here. So here's the L function given by that series. You can recover some very famous constants. Here's the Catalan's constants. So if you have parity for the value of this Catalan, you find that value. If you evaluate this L function at 2, you should find the same value. And you can see that this is really close, you just have a lack of precision in some sense. But you can increase the precision with a \p something, and you can have better approximation. Now, if you are interested in a number field, you can work with Dedekind data function, which is here. Here, the sum is taken over all the ideal of the integer ring, and you have this here. To define the Dedekind data function, you just give the polynomials that define your number field. Here, my number field is curve I. And again, the coefficient of my dual L function are the same than the original L function. My gamma factor is defined with two factors. One for the real zero. You can figure that this is the product of these two terms. And one for the number one. So the functional equation relates value at s and 1 minus s, and the conductor is 4. You can evaluate your L function at 2. We get this one. If you multiply by the number of Catalan, you will find this. And you can recover the same number by multiplying your function, by multiplying the zeta function with a Dirichlet series attached to 3, not 4. So we have that. I just put this line to show you that you can multiply two zeta function, two L function with alpha mode. In the same sense, if you want to add two L function, you can with alpha add. Okay, so you can do some operation with the L function quite easily. You can also divide one L function by another. Here, I'm trying to divide my Dedekind data function by the Riemann data function. And we get this number, so we can recover should be Catalan number. So we saw L function, zeta L function that we can define with a number field, but you can also define L function from an elliptic curve over Q or over a number field. Here it's over Q. In the exercise sheet, you will find an exercise over a number field. This is exactly the same kind of thing. Just you will have to specify. Here it's over Q, so I don't specify any number field here. If you want to look at your elliptic curve over a number field, you put a comma and the name of the number field. So I initialize this elliptic curve. We saw yesterday how to do. You create the L function. This. You can evaluate it at 1. You find something really close to 0. So 1 should be a 0 of this L function. Then I have a look at the first derivative is in 1, at 1. We still find something really close to 0. That means that 1 is a 0 of order at least 2. Try with the second derivative, it's still 0. So it's a 0 of order at least 3. Try with the next derivative. We find something which is not 0 anymore. So we just check that 1 is a 0 of order 3 of this L function. And you can check that the analytic rank of your elliptic curve is 3. And here, L from zeros of E will give you the series of zeros, and you also have a function named L called 0 orders of your L function, and you have just the order of the successive zeros. So here we can check that the rank of our elliptic curve is 3, And the zero of the L function at 1 is also 3. We checked the Birch and Swinnerton. I cannot tell that, but the BSD conjecture. Birch and Swinnerton diagram. So you can twist if you want your L function. So for that, you use L twist. Here I have my L function attached to an elliptic curve. And here I have my twist. So you just L twist. You get a new L function named L. Here are the first coefficient for the L function attached to E. Here are the first coefficient of the L function of this directed character. And here are the coefficients of my twist, the 10 first coefficient. You can see that this coefficient are the product of these two ones. So if I want to define the same curve over Q of theta 5, just beginning by initialize your number field here with the cyclotonic polynomial at 5. Don't forget to use another variable than x to avoid any problem. So this is my number field. To define the elliptic curve over this number field, I just specify the number field here. And I can create the associated L function. And if you just evaluate it at 2, you get this number. You can still twist it. And you can check maybe some quite known identities. So everything is quite instinctive, you know. You just have to be clear about what are your objects, but this is exactly the same process each time. You just define your main object and then often create this stuff and everything goes well. Sometimes you may want to use genus 2 curves instead of genus 1 curve. You can still have the L function of genus 2. The function to create them is a bit different. It's L genus 2, and this is not L create anymore. You specify the two polynomials that define your curve. Here we have x to the square plus x, and here it's polynomial. The output is the same. So here you have the coefficient for the dual L function. Here that defines the gamma factor. Then here you know that your functional equation relates value at s and value at 2 minus s, and this is your conjecture. You can evaluate it at some point in the same way as before, and you can get the first coefficient of the L function, the as before. So here we know that this L function will be 1 minus 2 over 2 to the s minus 2 over 3 to the s minus plus 1 over 4 to the s plus 0 over 5 to the s. You can also use L function. So here it's with the function L create. You specify your number, your ray number field. So we saw how to compute number field with additive information with BNF. Remember, it was to have class groups and units. So here I initialize the number field Q of square root of 23. If you want to use ray class groups, you need another initialization, which is BNR, R for ray. You give the number field, then your ray, your modulus. So here ray class group for modulus 1. you get a group of order 3, which is Z over 3Z. You can create your L function using your binaire structure here and the modulus. And you can have all you want with L1, which can still L1 AN if you want the coefficient and so on. And here, a function that I didn't mention previously, but I should do, it's algdep, which is in fact a way to find a polynomial of degree at most 3, for which exponential of z is an approximative root. So here you put your root bound on the degree, and it will give you a polynomial with integer coefficient. Okay, so it's a way to find minimal polynomial of approximation value. So we get that. You can also use Galois extension. So we saw earlier how to do. So I define my number field, and then I put I compute the Galois group. So here this extension is Galois, so we don't have any trouble. It's Galois of Galois group S3. You can, with Galois char table, get the table of the characters of G. So here, this is the table of the character. So it's defined over V. Your first character here, it's a trivial representation. The second here is a signature. And finally, you have a faithful irreducible representation of the dimension 2. So this is the character of S3. If you want to know how the conjugacy class are ordered, you can have the answer with Galois conjugacy. And we can then take our third character, so the faithful one, and compute the Artin L function associated. So here is L1 Artin, not L1 create, careful. And you need to give, so N was your number field, G is your Galois group. So here, number field, Galois group. This is the character that you want. So it was the first one, the third line of C. And this little o is an order, and I think I forget to mention it. No, but doesn't matter. So you have the same than before. So your N function, gamma factor, S related to 1 minus S, and this is the conductor. You can get the value of the first derivative of this N function as 0, you get that. And this is B. And if I try to find a polynomial with exponential of this number as the root of degree at most 3, we get this one. And we suggest that this function may be equal to a Haeckel function. And if you define that, you can check that you have the same first coefficient. Elfen check EQ. It will just okay, it's a technical matter that look at some okay, I don't want to say mistakes. I will look at the help documentation. I will say something wrong if I say like that. It was just for technical purpose, but I cannot remember why. Well, what you have to remember is just to define L function with parity P is quite easy. It's the same way almost always, except for artinal function, you have a specific function. For genus to curve, you have also a specific function. And for genus to curve, if your equation is at this shape, you just have to mention f. If you have two polynomials in X defining your genus to curve, you have to try to give the two polynomials beginning by this one. Don't switch. Okay, and after that, you have a lot of useful functions that you can. All these functions are, you can find the list of all the functions in the red card L function, which is not really big. Okay, it's not my computer, so I cannot show you, but you have the list of every function, and the same function works for every type of L function. So that's pretty useful. Well, I hope that I convince you that L function with PyGP is easy. After that, you can do anything you want with your L function, depending on the problem that you are looking at. And I will stop here. And before let you do the exercises, I want to thank you a lot for being here during all this week, for being really nice with me and so interested in what I was saying. I'm really happy to meet all of you. I know that some of you will leave today or tomorrow. I would have loved to spend more time with you, but well, maybe another year. And I will send you an email in the next days with some homeworks. You will have to fill a form for giving some feedback on all this lecture series. This is the first one, maybe the most important one, scientifically, in the point of view of science. I will also ask you if you agree to send me a family recipe, because I love to cook and I love Indian food. And I would be so happy if each one of you can send me a recipe translated in English, please. So that I can try to do by myself all your favorite food things. So this is the second homework. And for those of you that will still be here during the weekend or next week, if you want to go somewhere to show me your favorite place around, I would love to discover also the city and maybe the countryside. Well, so just do not hesitate to say me if you have a good idea, like going to the beach or maybe going to see that temple, or I don't know. So well, thank you by advance, and first fill the form because I need it. So you will find on the website an exercise sheet with only 4 or 5 exercises because I was late. So I'm sorry, I will keep working on it, but later. You can also do the last lecture exercises, and I will just be around. So just call me and ask your question. So thank you. It was great.